and gentlemen, today we will be doing the Unit 6 review for Algebra 2. This chapter focuses primarily on the operations of functions, so adding, subtracting, and multiplying and dividing functions. You also will have function composition, and going a little bit beyond all these function compositions is you are starting to get into more complicated functions such as polynomials, and so therefore we focus also on polynomial graphing. So up to this point we've been graphing absolute values, we've been graphing squares or quadratics, also known as quadratics, and now we're going one step beyond that and starting to graph things that have the power or the degree of 3 or the degree of 4 or degree of 5 or so on and so forth. Frequently you will get those higher degrees when you're adding, subtracting, multiplying, or dividing polynomials. So again, that's why we're kind of going to do the function operations. Now function operations will come up later in the packet, but right now we're just going to kind of focus on these polynomials. What are they? How do we put them in standard form? How do we graph them? So forth, so on. So the very first section here says standard form. Let me rotate that a little bit. There we go. So it says, write each polynomial in standard form, classify it by degree and number of terms. So first off, we need to understand what is standard form. Standard form basically says you want to put all of the different terms into an order from highest exponent to smallest exponent. So for example, sorry about that. The screen probably glitched a little bit. Just trying to make it a little bit more clear so you can actually kind of see it. So where was I? So I was talking about putting it in order from highest exponent to smallest exponent. So if you're looking at something like the very first example, you'll notice that I have an x to the third, an x squared, and an x. So right now it's all in kind of jumbled up order. So what I basically want to do is take the highest exponent, which is this negative 4x to the third. And yes, the number out in front is attached to the variable. So if I have a negative 4x to the third, that needs to go first. So I've kind of used this term. You can cross it out however you want. Then my next exponent would be this x squared. That is a positive x squared, so I'm going to go ahead and add that. Positive x squared. Go ahead and cancel that one out. You've used it. And then that leaves us with, last but not least, the 3x. So you can go through these. I will also say when you're placing things in order, standard form also says to combine like terms. So for example, in this particular one, you notice that you have this x to the third, but you also have another x to the third over here. So when you're trying to put x to the third first, you need to consider that you have two pieces here. So I have a negative 2 and a positive 1. Again, keep in mind that that's going to be a 1. So when I take negative 2 plus 1, that's going to give me a negative 1 x to the third. And then you also have a like term of 6 and negative 4. So the 6 and the negative 4 will just become a positive 2. So make sure you are combining like terms anytime that you can, and then writing them in the proper order. Now, the second part of the directions say classify it by degree and number of turns. Okay, so we need to figure out what is the degree, and then we use that degree to kind of figure out the turns. So first off, let's review what degree means. Degree means that even though you're looking at this and you see a 3, a 2, and a 1, some people would say you add it all together. That would be incorrect. The degree is simply saying what is the highest exponent. So I have a 3, a 2, and a 1. Between 3, 2, and 1, what's my highest exponent? My highest exponent is 3, so my degree is 3. I do want to remind you, if you go back and look at your notes a little bit more, if side example, if you have an example like this where it's an x squared y to the fourth plus x y to the sixth, then what you're going to be doing is saying, what's the degree here? And some people are like, oh, it's 6 because that's the highest exponent. But remember, you're considering what's the degree of each piece. The degree of this piece is the sum total. So the degree of this piece is going to be 6. The degree of this, keeping in mind that that's a 1, is going to be 7. So between these two degrees, 6 and 7, what's your highest degree? Your highest degree is 7. So kind of keep that in mind if you come across an example like that, you know, we are looking at the individual terms and saying what's the degree of that individual term, but then also overall looking at all the different terms, what's the highest degree, or what's the term with the highest degree? The highest degree is 7, so my degree would have been 7. So kind of keep that in mind. Then the number of turns, that's the easiest part. Turns is always just one left, one less. So if this is 3, this one's going to be 2. That's done. There's no real math there. It's always just one less than the degree. Some people may ask, like, well, how am I supposed to remember that? I would personally say that the degree is kind of, if you understand what a degree is, you can kind of quickly look at this and say what the degree is. The turn does not really come from anything in here. It's not saying, oh, like -4 or anything like that. It's not coming from this. It's coming from the degree. So once you're able to figure out the degree, just think one less. You can never go from the turn to degree unless you're given like a picture. Like if I were to give you a picture, something like this, right, and you see that it has 1, 2 turns, well, then you know it's probably degree 3. So just kind of keep that in mind. The only way you'd be able to tell turns is if you have the degree or if you're given the picture. The next section, fairly quick section. This section is basically saying determine the zeros. Anytime you hear that and it says, you know, find the zeros of this problem, find the zeros of this graph, whatever the case be, the zeros is always saying what value can I plug in for this x that will give me 0. So frequently when there's an x out in front, it's actually just going to be 0. But then inside here, it actually say what value of x could I plug in that would give me 0, and you would say -4. Now some people may say, well, I don't really understand where you got the -4 from, or maybe if you look at example 10, you see that it gets a little more complicated. You can also actually set up problems. So set up 4x minus 3 and say, what will make it equal 0? And even with the x plus 1, what will make it 0? And then it's just a matter of solving for x. So add 3 to the other side, divide both sides by 4, and you got your answer. Boom, that's what x equals. Same thing over here, if I subtract 1, boom, I got what x equals. So, you know, either way, some people can look at this and simply say, oh, I see the -4, it's going to be -4. Some people say it's the opposite of what's inside. That's fine. Some people actually need to set it up still. That's okay. I will also remind you, it says state multiplicities of 0. What that's basically saying is if you ever have something repeated or counted twice, make sure to mention that it's counted twice. So for example, this one up here, I have x plus 4 squared. So that squared technically says that I have it twice. So when I'm figuring out my answers, I should technically have an x minus 4 twice. Okay? Same thing if it's to the third. You know, this one's to the third. So when I figure out that x equals -8, I'm going to say that it's 3 times. Now there's many different ways that you'll actually see this. I highly recommend just writing out the words. That way you don't have all these crazy numbers within a given problem and you're like, what does this mean or what does that mean? If you just write out words, it's very clear that you're actually saying -8 3 times. I've also seen people write it out 3 times. That way there's absolutely no room for confusion because you have written it out 3 times. I have also seen some people that would say like this one squared. So some people would write underneath it double. Or I've seen times it by 2. Not a huge fan of the times it by 2, would not recommend it. Double is more of a popular one. Twice is another popular word. So kind of keep that in mind. Now, when it comes to graphing, a reminder that any of those even roots, we really just focused on in class double roots. But double roots mean that you're going to come down, hit the dot, and bounce back up. If it's a triple root, maybe I'll write 2 next to that. If it's a triple root, you're still going right through the point. If you go to a 4th power, like maybe this is x plus 1 to the 4th power, then you're still going to be doing that bouncing up. So even roots, you always kind of bounce. And then odd roots, you always go straight through. So kind of keep that in mind. That's why frequently if you just have one root, when you graph it, you're just going to go straight through that because it's an odd root. Other things to remind you of is 8 and 9, you will have to factor. So think about your greatest common factor in this case. So this one, I could pull a 7 out of both of these, and that's going to leave me with a 1 and a -4. If I pull an x out of both of these, that's going to leave me with an x squared. And if I pull an x out of this, it's going to leave me with nothing. I've now factored it. Now you have an x squared minus 4, which is the difference of perfect squares. So you can actually factor that a little bit more into a -2 and a +2, in which case now you see that you have an x here, an x here, and an x here. and you could kind of go from there figuring out yours. Number 11 and 12, nothing too rigorous here, just tedious. It's going to take you a while, and I'd really say go slow on these problems because it's very easy to kind of get overwhelmed or confused. But if you take it slow, it usually goes very well. So I would recommend just focusing on 2 at a time. It doesn't really matter what 2 you want to focus on. If you want to focus on the first 2 or the last 2, doesn't make a difference. It'll all work out the same. You are just going to go ahead and FOIL. So if I FOIL this first one, I'm going to 3x minus 1x minus 3. I still technically have that term on the end, so I'm just going to go ahead and write that out there for now. Keep working with this one until it's completely simplified, so x squared plus 2x minus 3. Now it is fully simplified. And the last step is still technically foiling. It's usually not it's not usually called foiling because foiling stands for first, outside, inside, last. This you can't really do first, outside, inside, last, but you can kind of think of it as saying this piece has to be multiplied by both of these pieces. So if I take an x squared and I times it by 3, and I times it by negative 1. So that's going to give me a 3x to the third and a minus 1x squared. Then I have to do it again with the 2x. I'm going to take 2x times 3 and 2x times negative 1. So that's going to give me a positive 6x squared, and then 2x times negative 1, negative 2x. And then last but not least, taking that negative 3 and multiplying it again by the 3x minus 1. So negative 3 times 3, negative 9x. Negative 3 times negative 1, positive 3. Once you've kind of everything got multiplied by everything, this piece got multiplied by both, this piece got multiplied by both, and this piece got multiplied by both. Everything got multiplied together. Then it's just a matter of going in and identifying your like terms. So I have a x to the third, I have an x squared, I have a 1x, and then I have a no x. So again, I kind of classified them. They do conveniently fall in order in this case, but that won't always happen. So the 3x is the only one of, 3x to the third is the only one of its kind. I then have a negative 1 and a positive 6. That's going to become positive 5x squared. Remember that when you are adding and combining like terms, keep the exponents the same. So this was an x squared, this was an x squared. Keep it an x squared, just figure out what's happening between the negative 1 and the 6. If I keep going, 2 and 9 would give you 11, and then the plus 3 is the only one of his kind to get you to your final answer. I will say that in the answer key, I kind of did it the other way, just because sometimes it's a little more organized to think that you're taking a 3x and multiplying it by each of these pieces, and then taking a negative 1 and multiplying it by each of these pieces. It doesn't really matter which order you go in. If you want to be thinking this to this, and then so forth, so on, or this to this, that's fine as well. So just kind of keep that in mind when you're working through those. Lots of different ways that you can solve those problems. Flipping on to the back side. Next up, we have write the polynomial function in standard form. We've already talked about standard form on the other side. It's basically saying simplify it all the way. I will say that when you're looking at these, frequently people look at these and they say, okay, well, it told me x equals 0, 0, negative 3, and 2. What does that even mean when it says x equals? It's the same idea as what we did over here. They're telling us that x equals 0. They're telling us that x equals negative 4. Anytime you see it twice, that probably means that it's squared. So key things like that to kind of pay attention to. I will say that the trickiest one for most people is usually this idea of x equals 0. Identifying it in this factored form is easy enough because you see the x all by itself and you can think it just equals 0. But when they give it to you in a form like this, frequently people say, I don't know what to do with the 0. You can think of it as saying x minus 0, in which case x minus 0 is still just an x. Okay? So however you want to kind of think of it, I think frequently people do a lot better with numbers, because if you know that x equals negative 3, then your factored form is probably going to be x plus 3. Because if I'm looking at a plus 3, like on the other side, if I flip back to the other side, if I'm looking at a plus 3, that means that x is going to be negative 3. Just like we said over here, it's usually the opposite. So if this was a plus 4, my answer is a negative 4. So on this side, what it's saying is my answer is a negative 3. So inside is going to be a positive 3. And then an x plus 2. Do keep in mind that this first one, this x minus 0, there was 2 of them. So that's going to need to be squared. If I think of that as just an x, I'm going to go ahead and square the x and have that x plus 3, x plus 2. I said that backwards. This one should be, I apologize, this should be a minus 2 because that's a positive 2. So since that's a positive 2, these are both going to be minus 2's. Now I will show you, just for the purpose of time, you can check out the answer key later. For this particular problem, once I have it written out, x squared, x plus 3, x minus 2, then you are going to want to FOIL it like we talked about in the other side when we talked about standard form. So I went ahead and just don't even worry about the x squared right now. Just FOIL these two pieces. Keep life simple. FOIL these two pieces. Get your simplified answer. And then at the very end, tack on that x squared, in which case each of these is going to get multiplied by an x squared, and you'll get your final simplified answer. Again, I remind you, for example, 14 is going to be a little bit longer, very similar to what we did on the other side where you're foiling 3 pieces, or distributing, however you want to say it. Multiplying 3 pieces together and getting a long piece like this. Please make sure standard form, you're writing it from highest exponent to smallest exponent. So kind of keep that in mind. You'll probably lose a few points if you're not paying attention to the order. Next up, it says write each function in factored form. The big recommendation I have here is please don't forget about GCFs. Greatest common factors. If you're looking at this and you're like, oh, I see an x to the third, I don't know how to factor an x to the third. Well, if you pull an x out, it's going to make your life a lot easier. I will also say, to make your life easier, also think about pulling out numbers. Frequently, if you have a number, an a, if you remember this was our a, our b, and our c. If you have an a, frequently you want to pull it out. Not always, but a lot of times it will make life easier. So for example, in 16, there is no a. A is just 1, so you don't have to really worry about pulling anything out there. But if you do have an a, see if you can pull it out. If I can pull out an a, for example, I can. That's going to leave me with a 1x squared. Over here, remember this is a plus 6, so inside it's going to now become a negative 3 because I pulled out a negative 2, leaving me with an x. And then over here, same thing with the 8, that's a positive 8, but I pulled out a negative 2, so what's going to be left over is a negative 4. Once you have that, not a huge fan of having the 1 written there, but for now I'll leave it there. You're going to ask yourself what numbers multiply to negative 4 but add to negative 3. That's going to be a negative 4 and a positive 1. Negative 4 plus 1, negative 3. Negative 4 times 1, negative 4. And then just don't forget your number out front. It is now factored, and that's all they kind of want you to do in this section. 17 is long division. So without kind of walking you all the way through it, I'll kind of verbally walk you through some stuff on the answer key. You can do this through synthetic division, so that's why I put on here long division. If you chose to do synthetic, that's perfectly fine. I just didn't put it on this answer key. You can always kind of look back in your notes at synthetic, or there's examples in the book you can check out. But long division basically says this. You are always trying to say, what can I multiply the very first variable, which in this case is an x, what can I multiply it by in order to get it exactly the same as this first piece? Now the reason we want it to be exactly the same is so that they will cancel out and go away entirely. So then I think, okay, I'm going to multiply it by an x squared. Now when you multiply it by an x squared, keep in mind that it's not just an x, it's an x plus 4. So when I say that I'm taking x squared and I'm multiplying it by this, I'm multiplying it by the entire thing. So when I take an x squared times an x plus 4, that will become an x to the third plus an x squared. Now you will next notice that I put a negative sign out in front here. This negative sign says that I am subtracting this entire piece. Please do not just subtract the x to the third, you are subtracting this entire piece. Just like the x plus 4 traveled together, just like when I said, oh, I'm taking this and I'm multiplying it by this, and I said, oh, multiply by the entire thing. When I'm subtracting, I am subtracting the entire thing. It travels as a giant piece. So this negative sign will ultimately get distributed, and making that a negative x to the third, Okay, perfect. That cancels out. It will also make this a negative 4. So when I take 6 minus 4, it leaves me with a 2. And then I bring down the 5x. Now my first term is this, 2x squared. So I have to ask, what can I multiply this piece by in order to get me to a 2x squared? Well, I'd have to multiply it by a 2x, of course. So I'm going to take 2x times this whole piece, and I'm going to get a 2x squared plus 8x. You will notice in this particular problem, the negative sign has already been distributed. So I gave this bad boy a negative, and I gave this bad boy a negative. They both got negative signs. They weren't there originally. It's only because I'm doing subtraction that they both got negative signs. Went ahead, these eliminated, and over here this gives me a negative 3. Next up, carry the 12 down. And again, last step, what can I multiply x by in order to get it to line up to this? Whatever happens over here happens, but I'm focused on this piece right here. Well, of course, I'd have to multiply it by a negative 3. So when I take negative 3 and I multiply it by both of these pieces, I'm going to get a negative 3x. Sorry, that's a negative 3x. Negative 3x minus 12. Then again, similar to up here, I went ahead and distributed a negative sign. So it turned it into a plus and a plus, because these were both negatives to begin with. And when I subtract a negative, it actually becomes a plus. Added these together and I got a remainder of 0. This is a good thing that I got a remainder of 0, because what that's saying is this is indeed a factor. So if they asked you, hey, is 4 plus x a factor of this whole thing? I'd say yes, absolutely. If it was a remainder of 1 or 2 or 3 or a million or a negative million, anything along that lines, anything other than 0, that means it is not a factor. No bueno, it is not a factor, and therefore you can't really proceed. Now you'll notice up here, if you're looking at the answer key, I kind of wrote the answer in factored form. So here's the x plus 4 they gave me, and here's the answer I got, x squared plus 2x minus 3. There it is. Now it says, can we factor more? This is very important, because if the directions say, please factor this all the way, this is not fully factored. This piece actually, x squared plus 2x minus 3, can be factored even more. Very similar to what we talked about up in these problems, in saying what numbers multiply to negative 4 but add to negative 3. That same process can happen here. What numbers can I multiply to negative 3 that add to 2? Well, that of course would be 3 and negative 1. So I have now factored this piece, the piece that we just solved for up here. I have taken this piece and factored it more. So that means that my final answer will have an x plus 3 and an x minus 1 and the original piece that they gave me, x plus 4. This is now fully factored, just like you guys would have had to do up here, except this one started out factored and you had to write it out. So it's just kind of working in reverse. One of them you go from the factored form to standard, one you're going from standard to factored. And the only way to really go from standard to factored is by them giving you one of the factors, because to figure out all three would be near impossible. But if they give you one, frequently you can find the other two. So kind of keep that in mind. And on to the graphing. This is going to be a long review, but I'm going to try to keep it as short as possible. So with the graphing, frequently it's nice when they give it to you in factored form, because you can kind of go right into the graphing. So first up, it says find the x-intercepts, also known as zeros. It's key to point out the fact that it says zeros, because we've done the zeros already. That was what can x equal, that will give me 0. So if I have an x plus 2, that means x is going to be negative 2. Please note the square, which means this is going to be a double. Frequently when I see double, I just put a d underneath. That way I don't forget about the fact that it's a double. Or you can write it twice, it's up to you. Then I have an x minus 1, which means I'm going to have a positive 1 and a positive 5. Now these are your x-intercepts, so that means they're going to be along your x-axis. So I can go ahead and put a dot at negative 2, 1, and 5, because I know that they're going to exist. Next up is the y-intercept. This is the tricky one that frequently people struggle with, but it's actually not as complicated as you need to think it as. Y-intercepts basically say this. Let me put a little y-intercept. They usually say that the x when you're thinking of a point x comma y, the x is always going to be 0. So what that says is if I come up here and I plug in a 0, so I have 0 plus 2, I have a 0 minus 1, and I have a 0 minus 5. Plug in a 0 and see what happens. Well, 0 plus 2 gives me 2, 0 minus 1 gives me negative 1, and 0 minus 5 gives me negative 5. Keep going. I now have a 2 squared. That's going to give me 4 times negative 1 times negative 5. Well, 4 times negative 1 times negative 5 should give me 20. So that means that my y is 20. Now, I obviously don't have 20 lines here, so I'm just going to call this point up here 0, 20. And it is kind of nice to label the y-intercept just because sometimes it's off scale. You know, that doesn't really look like 20 lines, especially if the lines are this big. So it's nice to kind of label it just to make sure everybody's on the same page. Next up, it says double roots, but we have already mentioned that. It's a double root. And then the very last one says end behaviors. Now, end behaviors, you may have to go back in your notes and review for a little bit, but I'll give you a quick crash course review. The big key things here is your leading coefficient. What is your leading coefficient? And what is your degree? Okay, well, the leading coefficient is usually the number that is way out in front. So my number that's way out in front, again, number, not variable, my number way out in front here is technically a 1. So if I say that my leading coefficient is 1, perfect. Then you go to the degree. Now, we did talk about degrees on the first page, but just a reminder, it basically says count how many x's you have. So I have an x. Remember that it's squared, so technically I have 2 x's. 3 x's, 4 x's, my degree is 4. Now you may be asking yourself, why do I need the leading coefficient and the degree? Please remember that the leading coefficient tells you what your right side is doing, and your degree is telling you what your left side is doing. Now the leading coefficient can either be positive or negative. This one in particular is positive, so that says my right side is going up. The leading coefficient, the degree, that is a matter of whether it's odd or even. My degree is 4, so that's even. That says that it's going to be the same. So if this one is up, this one will also be up. Now, if you take a second and you look at this graph, and this is not the answer, so do not copy this down. Or if you're watching, don't get confused, this is not the answer. If I look at this and I say that my right side is up, okay, and I do an up arrow, and then I start weaving, right? And I'm like, wee, and I have to go through that point, and then I come back down, and I'm like, boom, shakalaka. But then you look back over here and you say, well, wait a second, my left side was supposed to be up. What happened? Well, if you remember that negative 2 was a double root, that means at negative 2, when I come down, I actually just touch negative 2 and I bounce back up. So that's really why the left side is up, because of that double root. I will also recommend, this one kind of looks like it's pointy. Anytime you're doing a double root, make sure it kind of has some curve to it. All of your graphs should be kind of like wavy, not pointy. Okay, so don't do this whole pointy stuff. Try to make it kind of loose flowing as possible. I understand sometimes it looks like it's pointy, even though you tried waviness, and that's fine, I get it, but I'm just pointing it out. Do not be doing this whole like boom, 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 none of that. Make sure it kind of flows. It should all be kind of a smooth flowing line. Okay. Now I will say that occasionally you will run into examples that you need to factor yourself. So if I take a look at number 21, go ahead and factor it, pulling out your greatest common factor, which in this case is negative x. I then continue factoring it all the way through. The reason I wanted to show you this one is because this one has a leading coefficient that's negative. So you'll notice here that I said my right side goes down because my leading coefficient is negative. And actually looking at the answer key, I think I have this one backwards. Let's fix this one. So going ahead and kind of correcting this one, and you can see how quickly, one small little calculation can mess up a whole graph. So for example, I know that this one's down. This is when showing work is very important, because if you just did the graph, I really wouldn't be able to give you any credit because you just simply graphed it wrong, and that's wrong. Wrong is wrong. But if you showed me over here that your leading coefficient was right, I'd probably take off points because you know, you had that right, but you just didn't graph it right. So for example, my right side goes down, I start weaving in and out, and my left side starts going up, and I now have my correct final answer. So everything kind of switches around, everything kind of flips to the other side, again, just because of my right side was incorrect. And keeping in mind that, yes, my original one that I had wrong here, they were pointed opposite directions, so that's good with the -3 being opposite, odd. But because the right side starts down, my left side should have been up. So kind of doing those little self-checks. But keep that in mind, especially when graphing. And then on the last page, we get into the fun stuff. The last page has to do with all these function operations. Some big ones are, I would like to remind you that when you're looking at a problem like this, we are not saying that f and g, this is not f. So you can't look at this and say, oh, I have f plus g, that's going to be 4x minus 1, and then plus g, which is 2x squared plus 3. That is not true. That is not the case. That is very much not the case. What's really happening is you have f of x. You need f of x. This is not f of x. That is an f, in case you did not know that. I want to say, what is f of x? This is not f. This is an f and a g, not f of x. Two different things. These two things are not the same. But I can think and say, okay, well, here's an x. Why don't I kind of apply that to the f and to the g, right? So if I apply it to the f, I now have f of x. If I apply it to the g, I now have g of x. Once I have that, then yes, you are safe to go back to these problems, because f of x is a 4x minus 1, and g of x is a 2x squared plus 3. So in this particular example, it doesn't make a huge difference as to whether you're thinking of it as f plus g or f of x plus g of x. But I do need to stress that it's very important, because frequently people think, well, what happened to this x? And they're like, well, because I went straight into having the f and the g. But you do not have an f and a g. You have an f of x and a g of x. That is where the x is going. This x is being used to say, oh, it's f of x, not just f, it's f of x. It's not just a g, it's g of x. Once you have it defined as f of x, then you can go ahead and rewrite it. So that's where this x is going. This x is going to the f. It's going to the g, which allows you to then rewrite it as an f and a g of x. Now 24, that's already split up for you, so you don't have to really worry about that principle. You can kind of go straight into the math. One of the ones that I would like to point out is number 23. It doesn't say this in the directions, but you do want to think about restrictions. Restrictions basically say that when I go ahead and say I have g of x, 2x squared plus 3 over 4x minus 1, that's all fine. That's your answer. That's totally fine. But there is a restriction, because if you remember that denominators cannot be 0, because if you have a 0 on the denominator, it's not possible. So your restriction in this case would be actually saying, well, what if the bottom equals 0? Well, then I would have 4x equals 1, so x equals 1/4, right? So if I have a 1/4 and I plug it in here, that's going to give me 0. That's a problem. So what can x not equal? X cannot equal 1/4. So if you're thinking restrictions, and again, I will state that restrictions usually only happen when you have fractions. Not always, but a good majority of restrictions happen when you have fractions. So you really only have to worry about them for fractions. In which case, again, just look at the denominator and say that it cannot equal 0. You could even set it up like this and say 4x minus 1 cannot equal 0. The denominator cannot equal 0. And then solve it like a normal equation. Cannot equal 1, x cannot equal 1/4, and now you have your answer. So just kind of keep that in mind with fractions. I do want to remind you that if it's an open circle, that does not mean multiplication. That means that you are taking the g function and plugging it into f. So you can rewrite it like this. And then basically, there's two ways we talked about doing it in class. That's replacing the g of x, so keeping the f on the outside, but replacing the g of x with a 2x squared plus 3. Now the g function is gone. There's no longer a g at all in the problem, so you can just ignore g, and you can go to the f function. The f function is a 4x minus 1, but instead of an x, I'm going to have this. So wherever you see x, plug in a 2x squared plus 3. Once you have that plugged in, you can go ahead and simplify this term, distribute the 4, combine the 12 and the 1, and you got your final answer. So, however you want to remember doing that, some people just automatically go to the f function, and they say, here's my f function, let me get rid of the x and replace it with g. However you want to look at that. 29, you'll see on my answer key, I do stress the point that these are different because 27 is f with g inside. This one is g with f inside. You get totally different answers. So if you take a look at the answers, I get 8x squared plus 11. Over here I get a 32x squared minus 16x plus 5. There's really no relation because they're two totally different problems. Kind of keep that in mind. Number 28 and 30 are very similar to the 3-part one that we had on the quiz. And again, I stress to you, you can just kind of focus on the inside. So if we focus on 31, basically what this is saying is that you got to focus on g of 1, find g of 1, and I get 5. Well, then you say, okay, what do I do with this 5? This 5 then gets plugged in place of the g of 1. So I'll have f, and again, instead of g of 1, I'm going to have f of 5. So the 5 completely replaces the g of 1. The g of 1 is now gone, and there's only a 5 left. Now what I'm looking at is saying, what is f of 5? Well, I go into my f function, that's 4x minus 1, and I plug in a 5. Simplify that all the way through, and you're going to get 19. So really in these problems, start with the innermost and find an answer, get a number. So you're going to get a new number and work your way out, plug that into the next one. And then you'll get a new number and plug that into the next one. And then a new number, plug that into the next one. So after you use 1, really the heart of this, the 1, you're only going to end up using it once. You're going to use it for that centerpiece, that g of 1. But after you figure out what g of 1 is, you're never going to need 1 again because you have a new number that you get to work with. So kind of keep that in mind. Same thing with 28. Figure out what the inside is. You get a new number, plug that new number into the other function. And you're always going to be kind of working with that new number. And then last but not least, I know this is a long one, but it was 4 pages and I wanted to make sure I covered everything. This last one is finding the inverses, and you can kind of look at these problems in more detail, but I'll just kind of point some stuff out. Inverses basically say make sure you switch the x and the y first. That's the big thing, is just switch where the x's and y's are, and then solve for y. So if I'm looking at a particular problem, but if you're looking at any of these problems, if you see f of x, remember f of x and y are the same things. So frequently in all of these problems, I kind of went through and rewrote it with a y instead of an x. So I haven't started solving the problem yet. This up here is just me rewriting it. Same thing over here. I just rewrote the exact same problem, just instead of an f of x, I put a y. Once you do that, then you'll notice the squiggly line, I kind of broke it up because I've created a new problem now. I've switched the location of the x and the y. Please remember that when you switch the x and y, leave the numbers behind. So this 7 does not go with the x. You're just simply changing what variable you're using. So instead of having x here, I now have a y. Instead of having a y here, I now have an x. Once you get it like that, then you're going to need to use some of your math skills to figure out how to get y by itself. So for example, this problem is squared. How do you get rid of a square? With the square root. Hence the names, they're kind of related, square and square root. So this particular problem, I used a square root on both sides. I will say usually, and we talked about this in the past, anytime you square root something, try to have a plus or minus, just a small reminder. Once I've square rooted both sides, that leaves me with the 7y plus 2. I can subtract 2 and divide by 7. Remember that the subtracting 2 is on the outside of the square root. You did the square root before you subtracted, so they're going to be two totally separate things. But like I said, the rest of these problems you can kind of look through. 34 is very similar because you have a square root. So in order to get rid of the square root, you're going to have to square both sides, and then you can go ahead and bring the 7 over. But really, these are just kind of knowing some different tricks and ways to get y by themselves, knowing that if you have a fraction, you multiply it by its reciprocal, things like that, all good skills to remind or remember. And last thing that I'll say, and then I'll be quiet, is a reminder that inverse functions are always written as, it's still an f of x, it just has that -1. So if it was a g of x, I would have said g of x, but plug in a -1. If you forget to do that, it's not a big deal, at least for my class. In formality, you should definitely always write inverses that way, but at least for me, I'll know what you were getting at. You showed me the skill. You knew that you had to switch the x and y and solve, and that's enough to get credit in my class. But just keep in mind that technically inverses should have f of x. Just don't forget the -1 in there. All right, and that brings us to the end of Unit 6. Good luck and congratulations on finishing a 40-minute long video.